Hello everyone, today I'm going to present Jiffy, our multi-producer single consumer queue. It is weight-free, memory efficient and quite fast. We'll see it later in the graphs. I'm Dole Vadas and my advisor is Professor Ed Friedman and we're from the Computer Science Department, Technion, Israel. Let's start with talking about types of queues. We have the multi-producer multi-consumer queue, where multiple producers or enqueuers insert item into the queue and multiple consumers or enqueuers queue items, like this. And we have the multi-producer single consumer queue, where multiple producers feed requests to the same consumer, like this. So we have only one consumer or the queue. It is useful for sharded data processing system to delegate work to a single thread that is responsible to each shard to avoid costly synchronization while accessing a shard. And in data flow programming and load sharing applications, all of these need multi-producer single consumer queue. Lock freedom guarantees system-wide progress, while wait freedom is more appealing because it ensures that each operation always terminates in a bounded number of steps. And that's exactly what we did. So our queue is multi-producer single consumer queue. It is linearizable, it is wait-free, it is unbounded in the amount of items it can hold at any point of time, high performance and space efficient, which is desirable to any data structure, and it goes hand in hand with high performance when the data structure is small enough so that it can be placed mostly in the hardware caches, SRAM, and the access patterns are hardware cache friendly. We just gain in performance. Simple as that. Multi-producer, multi-consumer queues are the most general queues and therefore the most studied queues. However, they come at a premium since implementing wait-free multi-producer, multi-consumer queues requires to use help, where fast threads help slower threads to complete their operation. That's required to utilize complex helper data structures, which increase the memory consumption of such queues and limit their performance and scalability. Many such designs employ hardware cache unfriendly memory access pattern because they use pointers to access this metadata and jump from memory location to the other. So now let's talk about Jiffy's structure. As we said, we want to have a continuous access in memory, and therefore we used buffers or arrays. But because we want to be unbounded in the amount of items we can hold, we have a linked list of buffers. Each buffer is a buffer of nodes that hold data and an isSet flag to indicate if this node is ready to be dequeued. We have two pointers, head of queue and tail of queue. We have a global tail index that represents where is the end of the queue. It is an index, so here, for example, each buffer holds 6 items, so tail is 13. And this is the buffer list. We have the current buffer, next and prev pointers, head, and an index to indicate where the buffer in the queue. We try to be as frugal in memory as possible, so we allocate buffer as needed and delete once we dequeued all items in the buffer to hold only items that are really in the queue, that were enqueued and not yet dequeued. Let's talk about the basic operations or the naive implementation, and we'll start with enqueue. So to reserve a node, we simply perform fetch and add on tail, like this. In the example here, fetch and add on tail got us the index 4. 4 is already in the queue, already allocated, so it is now reserved for us. No other thread gonna touch this area in the memory, so it's not gonna interfere with the inserting process of our thread. When we finished inserting, we simply change isSet to set. In this example, we did fetch and add on tail and got 9. 9 is an index that is in a buffer that is not yet allocated and linked to the queue. So we need to allocate the buffer and link it to the queue. So we're going to allocate a new buffer and link it with a CAS. If the CAS succeeded, great for us. It means that we can insert our item. If it's failed, it means that another thread has succeeded with its own cache, so we can simply move to the new allocated buffer with the next pointer. Now 9 is a node that is reserved for us, and no other thread gonna interfere in the inserting process. And that's the enqueue operations. Now let's talk about the dequeue. Well, we have a single dequeuer or consumer, so we simply advance head by head plus plus to the next node like this and return the data of the previous node. Once we read an entire buffer, we can simply delete it like this. And then we can hold only items that are really in the queue and not yet dequeued. Well, this queue that we described so far is not yet linearizable. We're going to see some scenarios that breaks linearizability and see some tricks that we did to fix these scenarios. Let's start with the first scenario. We have two threads, T1 and T2, that enqueue two items concurrently. Because they both did fetch and add in the first step, T2 got the first index and T1 got the second one. T2 gets longer, and here in a point of time of T3, the dequeuer, T1 has finished the enqueuing process, so there is an item in the queue, X, and T2 is stalling. Now, if T3 will look at the head of the queue, it will see that ESET is empty, but it will be wrong to return an empty queue because there is an item in the queue, and therefore we need to scan the queue. So what we're going to do is, if the head is empty, we're going to scan the queue until reaching a set element or until we reach the end of the queue. If we reach a set element, we can return it because they're both, the head and this element were inserted concurrently, like this. So we scan and we can return the element and mark it as handled. Now ESET had three values: empty, set, and handled. When we read an entire buffer, we're gonna fold the queue like this. So this is the folding process. We're gonna hold only items that are really in the queue, that the item were inserted and not yet queued. So we saw the scan and the fold. However, one scan is not enough. We need to double scan. Let's explain why. We have three threads, T1, T2, and T3. T1 starts the inserting process by fetch and add on tail to reserve the first node. Now T2 starts the inserting process by performing fetch and add and reserving the second node. Now T3 starts the dequeuing. The head is still empty, so it starts the scan. It passed the first node, the second node, and not yet the third node. Now T2 is continuing the inserting process. Now it's finished the inserting process of Y in the second node and start the inserting process in the third node by fetch and add on tail, and now inserting Z. Now T3, the dequeuer, scan the third node. Well, it sees a node that is set, but it cannot dequeue it yet because Z was inserted after Y in T2. So it will be wrong to take out Z before Y. So what we're gonna do is scan again all the path from head till our nominee to be dequeued Z, like this. If something has changed in the path, there is a set element that is closer to the head, we're gonna mark this item as our new nominee. So Y now is our new nominee to be dequeued. We're gonna scan again from X all the path till Y and see if something has changed. Well, nothing has changed, so we can dequeue Y like this. Now we have another dequeue, so we're gonna scan again. This is the first scan. We're gonna mark Z as our new nominee, scan again, nothing has changed in the path, and we can dequeue our first nominee Z, like this. So this is some of our tricks. Let's look at the evaluation. We did an evaluation on two servers, Intel Xeon with 16 hardware threads and AMD PowerEdge with 128 threads, which have 4 NUMA nodes. We did different tests to each server. These are the tested algorithms. We have the weight-free queue, which is based on fetch and add and is weight-free. We have the LCR queue, which is based on fetch and add and lock-free, the CC queue, the MS queue, and a fetch and add to have an upper bound for all the queues that are fetch and add based. This is the total space usage. Let's look at the total heap usage. We can see the Jiffy is significantly lower than the rest of the queues. And now let's look at the hardware caches. We have the data caches D1 and D3. This is the number of misses. We can see that Jiffy has much less misses than the rest of the queues. That means that we use the caches better and therefore gain in performance. This is the benchmarks. First of all, we did each test 11 times and got the average. So each point is an average of 11 runs. With AMD Power Edge, we pin each software thread to a different hardware thread based on the NUMA nodes. So first of all, we filled an entire NUMA node and then moved to the closest one. With Intel Xeon, we tested up to 32 threads without pinning. And we have only 16 hardware threads. That means we have multiple threads per hardware thread. Now let's look at the graphs. Here it's the Intel Xeon with 10-second runs. We did 2 runs, one with 10-second run and a shorter run, 1-second run, to see the difference between a very long run and a very short run. We have an NQ only benchmark and multiple NQers with a single DQer. Jiffy is the blue line and fetch and add is the yellow line. As we can see, we have a big gap in the multiple NQers with a single DQer, and we're even faster than fetch and add. And remember that in Intel Xeon we have only 16 hardware threads. And if we look at the NQ only benchmark, we can see a big gap as well. And that's because we're more space efficient and we have access patterns that are more hardware cache friendly and less metadata. And all of this makes that even in the NQ only benchmark, we're much faster than the rest of the queues. Now let's look at the 1-second run. We have the AMD Power Edge and the Intel Xeon servers. We can see that in the AMD Power Edge, we have a very big gap with up to 128 threads, and in the Intel Xeon, we still reserve the gap. This is the NQ only benchmark. Now let's look at the multiple NQers with a single DQer with 1-second run. The gap is even bigger. We can see that in AMD Power Edge, we're close to the fetch and add, and in Intel Xeon, we passed the fetch and add with 16 hardware threads and software threads. Well, the takeaway from this is that we have a weight freedom without any helper algorithms and data structures, where a lower bound shown that it is necessary in multi-producer, multi-consumer queues. We have smaller metadata compared to the other queues. We have only 1 flag per item. Our access patterns are hardware cache friendly or more hardware cache friendly than the rest of the queues, which improve our throughput. And we have a queue operation that performs without any synchronization because it's the only one. No cast, no fetch and add. Which means that if your system needs a multi-producer single consumer queue, use multi-producer single consumer queue. Do not use multi-multi because you just lose performance. And that's that. Thank you very much.